Let's take a look at the first section here of chapter 7. It's called dilations. But before we get there, let's take a step back. Long time ago, we talked about how congruent figures have to have the exact same shape and the exact same size. Now, again, the way I just read that was a bit redundant, but that's for emphasis, okay? You can't have a triangle that's congruent to a square. But more than that, to say the two triangles are congruent, every pair of corresponding angles have to be congruent. Every pair of corresponding sides have to be congruent. Okay, so that's shape is, again, the number of sides, and then it's largely determined by angle measures. And size, that's determined by side length. Okay, but what we're getting in here with chapter 7 is the idea of similar figures. Now, again, we'll hit this again later with a more formal, more technical definition, but I want you to compare and contrast here. Similar figures have the same shape and proportional size. For example, I have an ordinary, nothing much special about it, quadrilateral ABCD, and I have the magic point X. Now I can do a transformation of this that goes with the topic from section 1 called a dilation. Again, it's such an important one. I come down here to the transform rule. We can do translations and rotations and reflections, and dilations is another option. So if I pick the figure and I pick point X is going to be referred to as the center of the dilation. That's a key bit of information that you need to know. And then we need the scale factor. So say I pick something simple like a factor of 2, boom. There's a figure that is similar to the original. Those two figures have the exact same shape, but clearly A prime, B prime, C prime, D prime has a bigger size. And again, it should be proportional. Now, if I so enjoy not doing this on paper, because if I take this center of dilation and I move that, I can actually separate the two figures. Okay, we're going to come back to this in a moment here, but I want you to see here for the length of segment AD. Oh, cross your fingers, it didn't round it off wrong. It did. There, that looks better. If the length of AD is 9, the length of A prime D prime is 18 because I used a scale factor of 2. Suppose I go back and I say I want to do another dilation, same figure, same center point, but now I want it to be 1/2. Now again, terms we'll get to later, but my goodness, are they obvious right now. If you have a scale factor that's greater than 1, it's called an enlargement. What you see right now, we had a scale factor that was less than 1. This is a reduction. Scale factor greater than 1 is an enlargement. Scale factor less than 1, it's a reduction. Again, at any point in time, you want to pause this video and take some notes on your own. That's why I'm making it a video. Now, let us also consider that if we have a scale factor of 1, it does nothing. You won't even be able to see it because it won't generate new points. It won't generate a new figure. Also, we're not going to use a scale factor of 0. Again, completely trivial. It would take whatever beautiful, wonderful, complex figure you have and reduce it down to a single point. We're never going to have a scale factor that's negative. Okay, so hopefully that all makes sense. So if we have anything between 0 and 1, it's a reduction. If we have anything greater than 1, it's an enlargement. Now, several things that you should notice here. Um, the center of dilation can be anywhere. Oh my goodness, if we pick a point there that's actually inside the figure, well, we're going to get something like this. Or maybe, where's it going? You could have a vertex of the figure as the center of the dilation, in which case that vertex isn't going to move, it's just the other ones. We could have that at any vertex. But what I also want you to see here is I'm doing this. Angle C and angle C prime are perfectly congruent. Angle D and angle D prime have to be congruent. Even if point X is way out here, corresponding angles are still congruent. The corresponding sides are the things that are proportional now. Okay. Let me do an even simpler one here. Let's just do a dilation of a segment. And I'm going to use, admittedly, not all that creatively. C is the center of our dilation. I can get a dilation in a couple of different ways using our basic tools. But step one, no matter what you do here, is by drawing rays. So from the center of the dilation, again, which I'm saying is C, I go through each vertex that I want to dilate. Okay, and again, I'm trying to keep this one here fairly simple and just dilate a segment. Now you will notice here what happens if I try and do a dilation of segment AB from point C and do a factor of, I don't know, let's try 1.5 this time. Point C, point A, and point A prime are all collinear. The same thing with the center, point B, and point B prime. If I try it again, say this original center here, and we go for, say, 0.25 as my scale factor. My goodness, that gets even smaller, okay, and closer to the center point of the dilation. Now, if you compare segment AB to the longer one here, A prime, B prime, and you compare both of those to the really short one here, you should notice that they are all parallel to one another. And again, moving the center of the dilation closer puts those images closer. And as if I change the length of one, it automatically changes the length of the other. And hopefully you can maybe get a better illustration here as I'm moving this around, that the original and its image stay parallel. Okay, let's take a look at some of the things they have here that I want you to understand. Now, they go through a couple of different ways that they want you to understand. Um, both of them start off with, again, rays. So if we want to dilate an entire figure, let's keep it simple like a triangle. So step one is we draw a ray from P to A. P, B. Draw ray P, C. Now they're saying here scale factor is 1/2 at point P. So then, well, 1/2, all we'd have to do is look at segment PB and find the midpoint, measure the half of that distance, and that's the location of B prime. Do that for all of them. Every vertex point, play connect the dots. You don't have to worry about the angles. Those will turn out to be congruent. You don't have to worry about the length of segment AB. The dilation will have the proper length. What you need to do is pay attention to the distance from the center. Okay. Now, that's not too bad. Method two, I think, is a bit trickier. It again starts by drawing rays. So in this case, centered at point Q, the dilation has a scale factor of 2. So we draw ray QW, QX, QY, and QZ. The first part there to figure out a vertex is going to be the same as before. We measure the distance from Q to W, multiply that distance by the scale factor, which in this case is 2, and measure that distance from Q on ray QW. That'll tell us where W prime is. Step 3, this is where I think it gets really tricky. From W prime, we put in a line parallel to the original segment WX. Where it meets ray QX, that's the location of X prime. Then we do it again. Through X prime, parallel to segment XY in the original, where that crosses ray QY, that's the location of Y prime. And then one last time through Y prime, parallel to segment YZ, where that intersects ray QZ, that'll tell us the location of Z prime. And then you just connect the dots there from Z prime back to W prime, and there's the figure. In this method, what they call method 2, the parallel method, you're measuring the distance from the center for just one point. With method 1, you had to measure the distance from the center for all of the vertex points. For here, all you have to do then is take distance and multiply it by the scale factor. Here, you're not multiplying by scale factor after step 2, you're putting in parallel lines. I'll leave it to you to decide which one's more of a challenge. But in the end, there are several key characteristics that are true for all dilations. Okay, now first of all, let's zoom in here. Here's our notation. Okay, capital D for dilation, and then in a subscript, we're going to put in parentheses two very, very important pieces of information. The first one there, N, is going to be our scale factor, comma, the second thing is going to tell you where the center of the dilation is. So again, we defined our previous transformations with reflections and translations and rotations and glide reflections as a process of mapping. So the first point there, a dilation will map point R onto, again, we're going to call it R prime, try and make sure that we understand the connections here. So it's on ray CR, again, point C is the center. So from the center to any vertex, the length of CR prime is equal to the length of CR multiplied by our scale factor N. The image of the center of dilation is the center itself. Again, C is C prime. We said this a little bit earlier here in the video. If N is greater than 1, it's called an enlargement. If we have anything less than 1, but still greater than 0, then we call that a reduction. Angles take care of themselves with this process. Every angle is congruent to its image, congruent. The side lengths are proportional, but the angle measures are congruent. And then that last line down there, suppose we put things on our coordinate plane here. So d sub n, if that's all they write, d sub n, that's the notation here where we're going to use the origin as the center of the dilation. Now again, a lot of this, they'll do it for you. Hey, what's going on here? Pay attention to the notation here. You're told rectangle A prime, B prime, C prime, D prime is a dilation with center P of ABCD. Now again, if there's similar figures, that implies ABCD is also a rectangle. We dilated one rectangle, we're going to get a new rectangle. So again, that process goes backwards too. How are the side lengths and angle measures of ABCD related to those of A prime, B prime, C prime, D prime? Okay, so hopefully you can count. The length of segment AB is 3 spaces. The length of segment A prime, B prime, okay, maybe a little bit not so obvious. 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. So what was our scale factor? Now, step 1 is not compare the angles. Step 1 is compare the side lengths. AB is 3, A prime, B prime is 9. BC is 2, B prime, C prime is 6. You're always going to, here, catch this, put the new measurement in the numerator. So 9 divided by 3 is 3. 6 divided by 2 is 3. Our scale factor here is 3. Again, new measurement in the numerator, new distance, new side length, however you want to think of that. The new one goes in the numerator, the original goes in the denominator. Because from the black one to the orange one, clearly this was an enlargement. Our scale factor has to be greater than 1. If you write the ratio upside down, you can't tell me from the black figure to the orange figure, this has a scale factor of 1/3 because this is an enlargement. All right, now let's go back to the angles there. What's the measure of angle A? 90 degrees. The measure of angle A prime, also 90 degrees. Again, corresponding angles are going to be congruent. Corresponding sides are going to be proportional. Don't forget that. Here, how ridiculous does this sound? we've got a scale factor. Oh, I forget what term. Okay, so n is equal to 3 in this case. So if the measure of angle A is 90 degrees, then the measure, oh, I'm going to start doing that. Measure of angle A prime, if we take the scale factor of 3 times 90, that's 270 degrees now. No, I mean, there's no, you're not going to have an angle inside a rectangle that's anything other than 90. Saying 270? No, never apply the scale factor to angle measures. Example 3, well, the only tricky thing here is direction. Quadrilateral J prime K prime M, sorry, L prime M prime is a dilation of JKLM. What's the scale factor? So if the new one is in orange, we have to find corresponding sides. Well, the 18 matches up with the 12. Remember, the new one goes in the numerator. So we take 18 over 12, always reduce. The scale factor is 3 halves. And yes, you can leave it as an improper fraction. It's absolutely fine. But again, from black to orange, it's an enlargement. Our scale factor has to be bigger than 1. Are you ready to do simple multiplication? Because that's really all we're going to do on this one. What are the vertices of, again, the notation there, capital D sub 3. This is a dilation centered at the origin with a scale factor of 3 of triangle ABC. Well, first thing we should do is probably what are the coordinates here? Okay, so here, if we zoom in on this bigger figure here, point A is at 2, negative 1. Point B is at negative 1, 2. And point C, right there on the x-axis, is at 3, 0. Our scale factor here is 3. You multiply every coordinate by 3. That's it. So A is at 2, negative 1. Well, 2 times 3 is 6. Negative 1 times 3 is negative 3. A prime ends up at 6, negative 3. B started at negative 1, 2. Well, negative 1 times 3 is still negative 3. 2 times 3 is still 6. B prime ends up at negative 3, 6. C is at 3, 0. 3 times 3 is 9. 3 times 0 is still 0. So C prime ends up at 9, 0. Plot those points, play connect the dots. There's the dilation, centered at the origin with a scale factor of 3. You don't have to, okay, angle A is congruent to angle A prime, but I don't need to do any calculations for that to make it happen. I would argue angle B is the smallest angle in triangle ABC. It's opposite from what, again, what I believe is clearly the shortest side, AC. So B prime is the smallest angle because A prime C prime is the shortest side. I'm not sure what the next thing is. You're done. So when they give you dilation centered at the origin here, find the coordinates and multiply repeatedly. That's all there is to that. And then as soon as you get used to that, then they move the center point. All right. Well, I mean, that's not that big of a deal. Again, they're also going to try and, for this first section here, especially, I want you to understand the concept. So they're not going to make these problems here exceedingly difficult. We're going to move it from the origin and we're going to use a vertex. For QRST, can we agree from the coordinates it's a rectangle? Okay. We're going to use one vertex of the rectangle as the center of dilation, and our scale factor here is going to be 1/2. No big deal. For segment RS, 1, 2, 3, 4, 5, 6 spaces long. Half of that would be 3 spaces. Again, you always measure, you always count from the center of the dilation, which in this case is point R. So we'll go in the direction of S, but we're going to stop at 3 spaces. Oh, look at the lovely chart that they've created for you here. This isn't the simple multiplication that we just saw a moment ago. Um, yeah, I think the chart's actually making it more complicated than it should. The distance from R to Q, 1, 2, 3, 4, 5, 6, 7, 8 spaces. So to get from R to Q prime, it's only 1, 2, 3, 4 spaces. And again, it has to be a rectangle. They're going through a complex process there to find the location of T prime. I really don't think that's necessary. Scale factors are used all over the place, such as blueprints. Blueprint for a new library uses a scale factor of 1 to 50. If we're measuring the reading space on the blueprint to find the actual dimensions and area, well, okay, here's our reading space. It looks like it's 14 centimeters by 12 centimeters. Well, what's 50 times bigger than 14? That'd be 700. What's 50 times bigger than 12? That'd be 600. Well, 700 centimeters, that is, which means 7 meters. 600 centimeters is 6 meters. So we have a reading space here that's 7 meters by 6 meters. And again, if you need to refer to the meter sticks in the front of the room, so again, part A was just asking what the dimensions are of the reading space. Part B says find the area. Well, if we just figured out, come on, second dot, here we go, that it's 7 by 6, that's 42 square meters. And that's pretty much it. Okay. We're going to dig deeper into similar figures here, but doing a dilation and understanding how things get transformed is a terrific place to start that conversation. So at this point, hopefully you've got some nice notes there for yourself. You can go over to the Realize website yourself instead of watching me. Click on a video of it, and I will see you all next week.